Welcome to the debate. So if I hand you a standard cherry gummy bear, right?
Okay.
But I blindfold you and firmly plug your nose right before you chew it, your brain will actually have absolutely no idea what flavor you're eating.
Yeah, it's just sweet.
Exactly. I mean, you'll taste the sugar, certainly. You'll feel that that distinct elastic rubbery texture on your teeth.
Right.
But without the visual confirmation of the red color, and without the olfactory stream of the artificial cherry scent,
You won't be able to name the flavor.
you just won't be able to name it. The perception completely breaks down.
It really does. And that sensory breakdown is exactly why we are here today. We're looking at a fundamental question of how human beings actually process and understand complex biology.
Right.
Do we decode these realities by physically interacting with them, like, chewing on a piece of candy? Or is that physical interaction just a clumsy, error-prone interface for what is in reality pure mathematical computation?
Yeah, and this central disagreement emerges from a truly fascinating array of source material. I mean, we're looking at everything from the use of simple gummy bears in cellular osmosis experiments, all the way up to the latest 2026 breakthroughs in AI neural decoding.
Right. It's a massive spectrum.
It is a massive spectrum of scientific modeling, and I will be taking the position that biological understanding is fundamentally an embodied physical process.
Okay.
I believe that tangible, multimodal representations like the physical properties of a gelatin matrix or, using the mouth for oral somasensory mapping, those provide the most profound and necessary insights into biological reality.
So we need to touch it.
Exactly. We need to physically touch the science to understand it.
Right. Well, and I will be arguing that while those physical heuristics are undeniably charming, they are inherently limited and, rudimentary.
Rudimentary?
Yes. True understanding of biological and neural processes is found strictly in the mathematical and electrical translations of computational models, and we see this evidence most clearly by modern AI decoders.
Well, to lay out my position, I think we have to look at history and how our bodies are tied to the physical world. Let's go back to 1922.
Oh, okay. Let's go back.
So, a man named Hans Riegel Sr. invented the gummy bear, or the dancing bear, right, in Bonn, Germany. And he used a gum base, originally gum arabic, that gave the candy this very specific, rubbery, elastic mouthfeel.
Yeah, the classic texture.
Right. Now, he was just making a treat for kids, but that exact physical tangibility is what makes it a perfect analog for microscopic biological reality.
Oh, so you're talking about how educators use them in the classroom.
Exactly. Educators use the gummy bear because its gelatin and sugar polymer matrix functions, astonishingly, like a semi-permeable cell membrane.
Okay, sure.
And because they come in all these distinct colors, we use them to tangibly map DNA base pairs and chromosomal recombination. My point is, this isn't just a convenient trick to keep students awake.
Right.
Biological processes are mechanical. They are spatial. So to really grasp them, our minds need an analog that physically mirrors that reality in a macroscopic way.
I come at it from a different way. I mean, I grew up playing with those molecular model kits and gummy bears and introductory science, and I appreciate the charm of it.
Yeah.
But those physical proxies are essentially training wheels. They are useful for a beginner, but ultimately they obscure the fundamental reality of biological systems.
Obscure it? Wait, how does feeling a model obscure the reality?
Because biological systems, at their core, are information processing engines. The true nature of biological decoding is computational. It is completely divorced from physical, rubbery analogies.
I don't see how you can separate them, though.
Well, if you look at the 2026 breakthroughs in neurocomputation, we have AI decoders that can map and reconstruct real-time visual perception, literally pulling actual moving video right out of the visual cortex.
Right. That's how life actually operates. Internal mental imagery and biological reality are best understood by analyzing how electrical signals translate raw stimuli. The gelatin matrix is a simplified toy.
Okay, but
The underlying mathematics of diffusion, or the electrochemical signaling of a neuron, that is the actual reality.
that's an interesting point, though. I would frame it differently, because when we look at that gummy bear in an osmosis experiment, It doesn't just represent osmosis as some loose poetic metaphor.
I mean, it kind of does. No, the polymer matrix actually physically mimics the mechanical reality of the cell. It gives us a grounded translation that abstract math just fails to communicate experientially.
But the mechanics are completely different.
Let's actually explore the step-by-step math and mechanics of this because it is deeply rigorous.
Okay, let's hear it.
If you take a gummy bear, you don't just toss it in a cup of water and watch it get big. You measure its initial mass. Let's say it's exactly 2.5 grams.
Right.
You prepare a series of solutions with very precise molarities of sucrose. Then you place that gelatin matrix into distilled water, which is hypotonic.
Meaning there is a higher concentration of water outside the bear than inside.
Right. The concentration of water molecules outside the bear is vastly higher than inside that dense, sugar-filled polymer matrix. So the math of osmotic pressure dictates that water is going to move down its concentration gradient.
Yeah.
Over 24 hours, as you watch, the bear physically expands. I mean, it can triple in mass to 7.5 grams. The water pushes into the matrix, expanding those structural bonds without actually breaking them.
Sure. And you could plot that expansion on a graph.
You plot it exactly. You graph the percentage change in mass against the molarity of the different solutions, and you find the exact isotonic point.
Right.
The precise moment where the line crosses the x-axis, where the concentration inside perfectly matches the outside. Feeling that swollen, tense gummy bear teaches the mechanics of turgor pressure in a cell membrane in a way that just staring at a mathematical formula simply cannot.
I'm sorry, but I just don't buy that. Let me tell you why.
Okay.
Equating a gelatin and sugar matrix to a living semi-permeable cell membrane is conceptually sloppy. It provides a false sense of understanding because it actively masks the actual mathematical and chemical complexities behind a rubber bear toy.
It doesn't mask them, it translates them into something the human brain can visualize.
No, it actually misrepresents them. Let's look at the mechanism you just described. Yes, the bear swells. Water moves down a concentration gradient, but a gelatin matrix is just a cross-linked polymer mesh.
Right.
It's basically a net. A real biological cell membrane is a dynamic, fluid mosaic of amphipathic lipid molecules.
Let's break that term down for the listener, though.
Right, so amphipathic just means these lipid molecules have a head that is attracted to water and a tail that repels water.
They naturally line up.
They naturally line up to form this highly specific fluid barrier. And that barrier is embedded with active machinery, things like voltage-gated ion channels and aquaporins, which are specialized protein channels designed exclusively for letting water through.
Right.
So when you teach someone using a gummy bear, they walk away thinking a cell membrane is like a sponge. It is not a sponge.
I agree. A cell is far more complex, but the physical expansion...
But it's fundamentally different. A cell uses active transport. It burns energy, ATP, to move ions against their natural flow. Think about the Nernst equation.
which calculates electrical potential.
Exactly. The Nernst equation calculates the electrical tension of a cell. It tells us how the cell acts like a microscopic battery, balancing chemical gradients with electrical charge.
Sure.
Or take the Goldman-Hodgkin-Cots voltage equation, which scales that math up to multiple ions to find the resting membrane potential. That math is the truth of the system.
But
The gummy bear only demonstrates passive diffusion through a porous solid. It completely ignores the electrochemical gradients that define actual living biology. You're mimicking a completely different mechanical process that just happens to look superficially similar if you squint.
But I would argue that this superficial physical modeling, as you call it, is precisely how our own brains are wired to understand the world.
How so?
We are not discrete calculation engines floating in a void. We process information through physical cross-modal integration.
What do you mean by cross-modal integration in this context?
Well, let's go back to the hook of our discussion, transitioning from basic cellular processes to human perception itself. Think about that experiment involving visual gustatory convergence.
Right, the blindfold test.
Yeah. If you take that 1922 gummy bear with its elastic mouthfeel and you chew it with your eyes and nose blocked, you experience an incredible phenomenon. The brain literally cannot parse the flavor.
You just taste basic sweet and sour.
Right. You perceive the sweetness on your tongue, maybe some acidity, and the rubbery texture, but you cannot identify it as a cherry or lemon gummy bear.
Yeah.
It is only when the visual and olfactory data streams are unblocked, when you can physically see the red color and physically smell the cherry scent, that the specific flavor is recognized by the brain.
Okay.
So my pushback here is, how can we claim biological understanding is purely abstract and computational, when the limbic system itself requires physically integrated, multimodal data streams to compute something as basic as taste? Our cognition is inextricably intertwined with physical sensory reality.
That's a compelling argument. But have you considered that the experiment you just cited proves the exact opposite point?
How could it prove the opposite? It shows the physical senses are required.
Because it proves that what we call taste is heavily computed. The physical candy, the gelatin, the sugar, the artificial flavoring is not the reality of the flavor.
It's the source of it, though.
No, the reality is the convergence of data streams in the limbic system. The physical gummy bear is just the raw stimulus. It is, frankly, just a delivery mechanism of molecules hitting your tongue. The brain is doing pure computation.
But it needs the physical properties to do it. You can't just compute nothing.
It needs data. When your eyes and nose are blocked, the computational engine is simply deprived of variables. The brain is running an algorithm to determine flavor.
An algorithm?
Yes, it takes gustatory input from the tongue, it takes olfactory input from the nasal cavity, and visual input from the optic nerve. It synthesizes those distinct data streams into a unified perception.
Okay.
The fact that removing the visual input breaks the perception of flavor demonstrates that flavor isn't an inherent physical property of the gummy bear that we just passively absorb. Flavor is a mathematical construct.
I think that's taking it a bit far.
It's generated by neural networks cross-referencing multisensory inputs against memory. The physical world is just throwing photons and molecules at us. The truth of our reality is the computation happening in the brain.
And yet, we use that exact physical sensory integration to bypass the limitations of broken neural pathways. Let's look at the ultimate frontier, restoring or reconstructing sight.
Okay.
If the brain were purely an abstract computer, we would only interface with it via code. But instead, researchers champion tactile neurocomputation.
Oh, you're talking about the 3D printed models for the visually impaired?
Yes. Think about how incredibly sensitive your tongue is. I mean, you can feel a single microscopic grain of sand in your mouth.
Very true.
Researchers have taken advantage of that exact physical sensitivity by 3D printing specialized protein-mimicking candy gummies. Because of the brain's incredible neuroplasticity and cross-modal mapping, blind students can literally see complex molecular shapes and visual dimensions directly via oral somatosensory pathways.
Using the mouth to map out tactile information?
Exactly. Just as we use multicolored bears to physically map DNA base pairs, these 3D printed gummies map visual dimensions into a physical language the human body can natively process.
Right.
The mechanoreceptors on the tongue send the physical shape to the brain, and the brain visualizes it. We are using the physical tactile properties of a gummy matrix to upload visual data. This tactile neurocomputation proves that the physical, embodied interface isn't just a training wheel, it is a primary, profound pathway for biological decoding.
I acknowledge the ingenuity of tactile models. It is a brilliant use of neuroplasticity. But honestly,
Yeah?
it is fundamentally a primitive workaround compared to the 2026 AI breakthroughs in neurocomputation. We need to explore exactly how neurocomputation decodes visual signals from the brain today, because we are moving way beyond the tongue.
But the tongue works because it's embodied.
Sure, but look at the scale of what we can achieve when we bypass the physical interface entirely. We are using AI decoders to map and reconstruct real-time visual perception directly from the neural activity firing in the visual cortex.
Right.
Let's break down how this actually works. The subject watches a movie. While they watch, an AI monitors their functional MRI data. Specifically, it's looking at localized blood oxygenation level dependent signals.
Wait, explain how that blood flow translates to an image, though, because that's a huge leap for the listener.
Gladly. So when neurons in your visual cortex fire in response to seeing a shape or a color on a screen, they need energy,
Okay.
which means they draw oxygen-rich blood to that specific area of the brain. The fMRI tracks exactly where that blood is flowing in real time. Think of it like reverse engineering the code of a complex video game just by watching the heat given off by the computer processor.
Oh, wow.
Right? The computational vision models take those electrical signals and run them through generative AI. The AI translates that map of brain activity, the latent space, into an actual pixel-by-pixel video output.
It's incredible.
We can literally see what the person is seeing internally on a monitor. We have cracked the exact computational code of how raw stimuli become internal mental imagery. We don't need a physical analog to understand what the brain is doing. We have the mathematical key to the cipher.
I'm not convinced by that line of reasoning because you are completely ignoring the genesis of the data.
How am I ignoring it? The data comes directly from the visual cortex.
Right, but even an AI reconstructing a real-time movie from the visual cortex still requires the initial raw physical stimuli to trigger those electrical signals in the first place.
Well, yes, but...
You cannot train those 2026 AI decoders without first exposing the human subject to the physical optical world. The AI is learning the mapping between the physical reality and the neural electrical representation. Therefore, the physical embodied world remains the inescapable foundation of all biological computation.
But the end result is an abstraction.
An abstraction derived from a physical reality. You call the tactile gummies a primitive workaround, but they operate on the exact same fundamental principle.
How?
The brain evolved to process physical space, texture, and light. When you translate abstract protein structures into a physical gummy that a blind student can explore with their tongue, you are honoring the evolutionary reality of the biological machine.
I see what you're saying, but...
The grain is an embodied organ. Trying to understand it purely as an abstract mathematical model strips away the context of its existence. It's like trying to understand the ocean by only looking at the chemical formula for H2O. You miss the currents, the pressure, the physical reality of the system.
But understanding the chemical formula of H2O is exactly what allows us to predict how it will behave in any environment, on any planet, under any pressure. That is the profound power of abstraction.
Okay, but...
When we rely solely on physical heuristics, we are bound by the physical limitations of those heuristics.
Limitations like what?
Well, you brought up the multicolored gummy bears used to map DNA base pairs and chromosomal recombination.
Yeah.
That is a perfect example of where physical models break down and fail the student. A red gummy bear represents an adenine, a yellow one represents a thymine. A student physically pairs them up on a desk. But DNA is not a static ladder of colored candies.
Well, nobody thinks it's literal candy.
But the physical model creates a static mental image. DNA is a highly dynamic, coiled, shifting molecule governed by electrostatic forces, quantum tunneling and proton transfers, and complex topological winding.
Right, it's complex.
When we look at DNA computationally, we can simulate protein folding. We can model CRISPR-Cas9 off-target cleavage with atomic precision. We can decode the entire human genome in hours.
Yeah.
We could never achieve that level of biological decoding if we insisted on physically modeling it with gelatin matrices. The 2026 visual AI decoders do not care about the physical eye. They care about the information geometry of the visual cortex. By isolating the computation from the physical hardware, we achieve true decoding.
But abstraction without physical grounding often leads to profound misunderstandings, especially in biology, which is messy, redundant, and deeply physical.
Is it, though?
Yes. The tactile gummy protein models aren't meant to replace the quantum calculations of protein folding. They are meant to allow human cognition, which, again, is physically embodied, to grasp the spatial reality of the molecule.
Right.
The blind student utilizing those oral somosensory pathways to feel the groove of a receptor site is engaging a part of their neural architecture that evolved to understand 3D space physically. That student gains an intuitive, spatial understanding of how a molecule binds to a receptor that a purely mathematical output simply does not provide to human consciousness.
Well, but it's prone to error. Let's return to the visual gustatory experiment. When you block the visual and olfactory streams, the subject experiences a complete breakdown in perception.
Because they are missing data.
Exactly. To you, this highlights the necessity of the physical senses. To me, it highlights the absolute fragility of the biological hardware. Our biological decoding mechanisms are so easily fooled.
Well, sure, illusions happen.
We experience optical illusions. Our taste is literally manipulated by food coloring. Why would we want to anchor our ultimate scientific understanding to the very physical systems that are prone to such easily demonstrated errors? The abstract mathematical models of neurocomputation don't suffer from visual gustatory confusion. They simply read the data.
They read the data that the physical system produces. You cannot separate the dancer from the dance here.
I think you can.
No, those mathematical models are reading the localized blood oxygenation levels. That is physical fluid mechanics. And that blood flow is driven by cellular metabolism, which is physical chemistry.
Right, but
The AI decoder is a brilliant tool, but it is a tool used to interpret a deeply physical, embodied reality. And when we try to communicate that reality, whether it's to a student learning cellular osmosis or a visually impaired person learning molecular biology, translating it back into a physical, tangible analog like a gelatin matrix bridges the gap between the microscopic truth and macroscopic human cognition.
it bridges the gap, certainly, but only as a temporary scaffold. Once the structure of understanding is built, the scaffold has to be removed to see the building clearly.
I just don't think you can ever fully remove it.
I disagree. The 1922 dancing bear was a wonderful invention. Its utility in the classroom is undeniable. But as we move beyond 2026, as our AI decoders become more sophisticated at translating the latent space of the brain directly, we will find that we rely less and less on physical analogies.
You really think so?
Absolutely. We will understand the brain not as a physical object to be poked and prodded, but as an informational landscape to be mapped and decoded.
Well, as we draw this discussion to a close, I think about the profound spectrum of scientific modeling we've traversed today. From the simple, elegant swelling of a gelatin matrix demonstrating the mechanics of osmosis to the oral somatosensory pathways allowing the blind to see proteins, it is clear to me that biological understanding is inherently anchored in physical, tangible reality.
We are physical beings. Our deepest insights often come when we can touch, see, and physically interact with a representation of the microscopic world.
And while I can see that physical proxies like the gummy bear are highly useful pedagogical tools, I maintain that the definitive future of decoding biology lies in abstract neurocomputation.
Right.
The mathematical principles of cell biology and the sheer power of AI decoders reading the exact electrical signals of the visual cortex demonstrate that true understanding transcends physical heuristics. We are moving toward a future of pure informational clarity.
Yet in many ways we find a remarkable point of convergence here. Whether a scientist is using a 1922 German candy or a 2026 AI decoder, both approaches share the exact identical goal:
Translating the mysterious, invisible processes of biology into decipherable formats.
Exactly. They are two different languages attempting to translate the same profound biological text.
And the incredible depth of the source material we've explored today suggests that the ongoing evolution between physical analogs and neural computations offers so much more for all of us to explore.
Absolutely. The next time you see a simple piece of candy, ask yourself, are you looking at a child's treat or a highly calibrated matrix that physically mirrors the secret architecture of human perception?